On the morning of March 7th, 1943, beneath the cold grey skies of southern England, a lone figure stood in a muddy field, surrounded by twisted metal, discarded engine parts, and machinery that most people would have dismissed as worthless scrap. The wind carried the smell of oil and rust across the airfield, where damaged aircraft sat in various states of disrepair, waiting for parts that might never arrive. Lieutenant James Hartford, a 28-year-old mechanical engineer from Detroit, Michigan, looked at the collection of broken equipment with eyes that saw something entirely different from what everyone else perceived. The German military leadership believed their opponents were running out of time, that the mounting losses of aircraft and equipment would eventually cripple Allied operations. They could never have imagined that one man with a toolbox and an unconventional mind would prove them catastrophically wrong. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. This is the remarkable account of how ingenuity, determination, and a refusal to accept limitations transformed what others saw as garbage into something that would leave experienced German pilots shaking their heads in disbelief, forcing them to question everything they thought they knew about their enemy's capabilities. James Hartford had arrived in England 6 months earlier, part of a specialized engineering unit, tasked with maintaining and repairing equipment at a forward airfield in Somerset. The journey from America had been long and uncomfortable, crossing the Atlantic in a convoy that zigzagged through dangerous waters, every man aboard acutely aware that enemy submarines prowled beneath the surface. James had spent most of that voyage in the engine room of the transport ship, helping the overworked crew keep the aging vessel running, his hands perpetually stained with grease, his mind constantly working through mechanical problems. Growing up in Detroit had given James an education that no university could match. His father had worked at the Ford plant before the economy collapsed, and from the age of 7, James had spent his afternoons in garages and workshops, learning to coax life from engines that others had written off as beyond repair. By the time he was 14, he could disassemble and rebuild a carburetor blindfolded, diagnose engine trouble by sound alone, and fabricate replacement parts using whatever materials were available. His talent had earned him a scholarship to study mechanical engineering at a small college in Ohio, where he had graduated at the top of his class in 1938. The world James graduated into was one of increasing tension and looming conflict. Europe had already begun its descent into darkness, and by the time Pearl Harbor was struck in December 1941, James had been working at an aircraft manufacturing plant in California, helping to design and improve production techniques for training aircraft. When he enlisted in early 1942, his skills were immediately recognized, and after completing officer training, he was assigned to a maintenance and repair unit destined for overseas deployment. The airfield where James now served was home to a squadron of medium attack aircraft, used primarily for tactical operations against German positions along the French coast. These missions were dangerous, flying at low altitude to strike specific targets, and the aircraft frequently returned with significant damage. The problem was that replacement parts took weeks, or sometimes months, to arrive, and the official procurement system moved at a pace that seemed designed to frustrate everyone involved. Forms had to be filled out in triplicate, requests had to be approved by multiple levels of command, and even then, there was no guarantee that the parts would actually arrive. Major Robert Thornton, the squadron commander, was a career officer who had been flying since 1936. He was a competent pilot and a decent leader, but he was also a man who believed firmly in following established procedures and maintaining proper military order. When James first suggested that they might be able to repair damaged aircraft using improvised methods and salvaged materials, Thornton had been skeptical to the point of dismissiveness. "You want to rebuild aircraft using junk, Lieutenant?" Thornton had asked during their first meeting in his office, his tone making clear what he thought of the idea. "These are precision machines, not farm tractors. Everything has to meet exact specifications. One improperly installed component could bring down an aircraft and take the crew with it." James had expected this reaction. He had encountered it throughout his life, the assumption that because he was self-taught in many areas, because he came from a working-class background, because of the color of his skin, He couldn't possibly understand the complexities of modern machinery, but James had also learned that the best response to skepticism was not argument, but demonstration. "With respect, sir, I understand the risks," James had replied calmly. "But I also understand that we currently have 7 aircraft grounded because we're waiting for parts that won't arrive for at least 6 weeks. In that time, we could lose more aircraft, which means even more machines sitting idle. I'm not suggesting we compromise safety. I'm suggesting we find creative solutions that meet the necessary standards while using available resources." Thornton had studied James for a long moment, his expression unreadable. Finally, he had nodded slowly. "All right, Lieutenant. You have 1 week. Pick 1 aircraft and show me what you can do, but understand this: if your repairs fail, if a crew is endangered because of improvised equipment, you'll be on the first transport back to the States. Understood?" James had understood perfectly. He also understood that this was likely the only chance he would get. The aircraft he chose was a medium attack plane that had returned from a mission 3 weeks earlier with extensive damage to its hydraulic system. Shrapnel from anti-aircraft fire had severed multiple lines, destroyed the main pump, and damaged several control mechanisms. The official repair estimate required 17 different replacement parts, most of which were currently unavailable. According to the maintenance log, the aircraft was scheduled to remain grounded for at least 2 months. James spent the first day simply studying the damaged systems, taking detailed measurements, making sketches, and examining every component. He worked alone in the hangar, often staying well past midnight, his only company the sound of wind rattling the metal walls and the occasional visit from Sergeant Michael Chen, a Chinese-American mechanic from San Francisco who supervised the regular maintenance crew. Chen was a 35-year-old veteran who had been working on aircraft since before the conflict began. He had initially viewed James with the same skepticism as everyone else, but he was also a practical man who respected competence when he saw it. On the second night, as James was making calculations by the light of a single work lamp, Chen brought him a cup of coffee and sat down on a nearby toolbox. "You really think you can fix this?" Chen asked, nodding toward the damaged aircraft. "The hydraulic system is completely shot. We've been waiting for parts since early February." James looked up from his notes, gratefully accepting the coffee. "I know I can fix it. The question is whether I can fix it in a way that meets safety standards and satisfies Major Thornton." Chen smiled slightly. "Thornton's all right. Tough, but fair. He's just scared of taking responsibility for something unconventional. If you can prove your repairs are solid, he'll back you. The trick is getting him to trust the proof." Over the next several days, James began gathering materials from across the base. He visited the scrapyard, where damaged equipment was stored awaiting disposal. He examined wrecked aircraft that had been written off as beyond repair. He talked to mechanics from other units, learning what they had in surplus and what they needed. Slowly, he began to assemble a collection of components that most people would never have considered usable. From a crashed aircraft that had been sitting in the scrapyard for months, he salvaged sections of hydraulic line that were still intact. From a damaged truck, he obtained fittings that could be modified to work with the aircraft system. From the machine shop, he acquired raw materials, steel rod, aluminum sheet, brass fittings that could be shaped into custom parts. He even traded a bottle of whiskey to a supply sergeant at a nearby army base in exchange for several pounds of high-grade rubber that could be used to fabricate new seals and gaskets. The actual repair work was meticulous and exhausting. James fabricated a replacement hydraulic pump, using the housing from the damaged original unit, internal components salvaged from 3 different sources, and custom-made parts that he machined himself in the base workshop. He created new hydraulic lines by carefully cutting, flaring, and joining sections of salvaged tubing, testing each connection for leaks under pressure. He rebuilt control mechanisms by hand, replacing damaged gears and linkages with components he crafted from raw materials. Sergeant Chen watched the work progress with growing amazement. By the 4th day, he had assigned 2 of his best mechanics to assist James, and word had begun to spread around the base about what was happening in the maintenance hangar. Pilots and crew members found excuses to walk past, curious to see the aircraft that was supposedly being rebuilt from scrap. On the morning of the 7th day, James completed the final connections and prepared to test the hydraulic system. Major Thornton arrived at the hangar with Captain Donald Miller, the squadron's chief engineer, a Harvard-educated officer who had spent 3 years designing aircraft for a major manufacturer before the conflict began. Miller was known for his exacting standards and his insistence on proper procedures. If anyone was going to find fault with James's work, it would be him. "Show me what you've done, Lieutenant," Thornton said without preamble. For the next 2 hours, James walked them through every repair, explaining his methodology, showing them his calculations, demonstrating the strength and reliability of each component. He had prepared detailed documentation showing that every repair met or exceeded the specifications for the original parts. He had tested each system multiple times, checking for leaks, measuring pressures, verifying response times. Captain Miller asked technical questions, challenging James's decisions, probing for weaknesses in his approach. James answered each question calmly and thoroughly, backing up his explanations with data and demonstrable results. As the inspection continued, Miller's expression gradually changed from skepticism to something approaching respect. Finally, Thornton turned to Miller. "Well, Captain, what's your assessment?" Miller was quiet for a moment, still studying the rebuilt hydraulic system. "Honestly, sir, it's remarkable. Not only has Lieutenant Hartford solved the immediate problems, but some of his solutions are actually improvements over the original design. This custom pump housing, for example, it's more accessible for maintenance and uses a more efficient bearing configuration. If I didn't know better, I'd say this came from a factory." Thornton nodded slowly, then looked at James. "All right, Lieutenant, we'll do a full systems test this afternoon, and if everything checks out, we'll do a test flight tomorrow. If the aircraft performs as it should, I want you to assess every grounded plane in the squadron and tell me which ones you can repair using similar methods." That was the beginning. Over the next 3 months, James and his growing team, eventually including 6 mechanics and 2 other engineers, brought 11 grounded aircraft back to operational status. They fabricated replacement parts, improvised solutions to seemingly impossible problems, and developed techniques that would eventually be adopted by maintenance units across the theater of operations. But the real test came in June, when the squadron received urgent orders for a major operation requiring maximum aircraft availability. The target was a heavily defended German supply depot near the French coast, and the mission required every available plane. Thanks to James's work, the squadron launched with 14 aircraft, 7 more than would have been possible using conventional repair methods. The mission was successful, destroying significant amounts of enemy supplies and equipment, but 3 aircraft returned with heavy damage. One plane, flown by Captain Thomas Anderson, a 25-year-old pilot from Iowa, had taken multiple strikes from anti-aircraft fire. The right engine was destroyed, control surfaces were severely damaged, and the landing gear had been hit. By all conventional assessments, the aircraft was a total loss. Anderson and his crew had barely survived the flight back to England, nursing the crippled aircraft across the channel, fighting to maintain altitude, praying that the structure would hold together long enough to reach friendly territory. When they finally touched down, or rather crashed in a controlled manner onto the airfield's grass alongside the main runway, the entire squadron had gathered to watch, certain they were witnessing the end of that particular aircraft's service life. James was among those watching. As the damaged plane came to rest and the crew scrambled out, shaken but uninjured, he was already walking toward it, his mind cataloguing the damage, considering possibilities. Major Thornton intercepted him before he reached the wreck. "Don't even think about it, Lieutenant," Thornton said, though his tone was more resigned than firm. "That aircraft is done. We'll salvage what we can for parts, but nobody's flying that machine again." James stopped, looking past Thornton at the damaged plane. "With respect, sir, may I at least examine it thoroughly before we make that determination? I understand it looks bad, but I'd like to assess the structural integrity and see what's actually salvageable versus what just looks terrible." Thornton sighed. "You have 48 hours to evaluate it. But Hartford, be realistic. Some things really are beyond repair." The aircraft that James examined over the next 2 days was indeed severely damaged. The right engine was completely destroyed, holed in multiple places by shrapnel, with the propeller bent beyond any hope of repair. The right wing had taken several strikes, compromising structural members and tearing large holes in the skin. The landing gear had been damaged to the point where the right main wheel was canted at an obvious angle. The fuselage showed multiple impact points, and several control cables had been severed. But as James worked his way through the aircraft, making measurements, testing structural components, examining the actual damage beneath the dramatic exterior appearance, he began to see a path forward. The left engine was completely undamaged. The main structural spars in both wings were intact. The damage was primarily to secondary structures and skin. The fuselage frame was sound. The control systems, while damaged, could be rebuilt. Even the landing gear, which looked hopeless, was actually repairable with some creative metalwork. James spent hours in the base machine shop, studying the damaged components, taking precise measurements, calculating stresses and loads. He visited the scrapyard again, examining every piece of equipment available. He sent requests to other bases, looking for specific components they might have in surplus. He even wrote to the aircraft manufacturer, explaining the situation and asking for technical advice on non-standard repairs. By the end of his 48-hour evaluation period, James had developed a comprehensive repair plan that was equal parts engineering, improvisation, and sheer audacity. When he presented it to Major Thornton and Captain Miller, both men were stunned by its scope. "You want to remove the damaged engine and replace it with one from a training aircraft that crashed last month?" Miller said, reviewing James's documentation. "That engine is from a completely different aircraft type. The mounting points don't match. The power output is different. The propeller hub is a different specification." "I know," James replied calmly. "That's why I'm proposing we fabricate a custom engine mount, using the original attachment points on the airframe, and a new intermediate structure that adapts to the different engine. The power output is actually slightly higher than the original, which will compensate for the additional weight of reinforcement materials I'll need to use in the wing repairs. As for the propeller, I found one in storage at an Army airbase 30 kilometers from here. It's from a different aircraft type, but the specifications are close enough that with some modification to the hub, it will work." Thornton was shaking his head in disbelief. "And the wing repairs? You're talking about essentially rebuilding a quarter of the wing structure using material from 3 different sources." "Not rebuilding, sir. Reinforcing and repairing," James corrected. "The main spar is intact. I'm replacing damaged ribs with fabricated components made from aluminum sheet and angle stock. The skin will be patched using material from a written-off aircraft in the scrapyard. The repair will actually be stronger than the original structure, because I'll be adding reinforcement to the damaged areas." Captain Miller leaned back in his chair, studying the young engineer. "Lieutenant Hartford, what you're proposing is essentially designing and building a hybrid aircraft using parts from multiple sources and custom fabricated components. Even if it's technically possible, and I'm not certain it is, the amount of work involved would be enormous. We're talking about hundreds of hours of labor. Is it really worth it for one aircraft?" James had prepared for this question. "Sir, it's not just about one aircraft. Every plane matters, yes, but what really matters is proving that we don't have to accept the limitations of the current supply system. Right now we're grounding aircraft because we can't get specific parts through official channels. But if we can demonstrate that skilled mechanics and engineers can solve these problems using available resources, we change the entire equation. We make ourselves less dependent on supply lines that take weeks or months to deliver. We keep more aircraft operational, which means more effective operations, which means saving lives." There was a long silence. Finally, Thornton looked at Miller. "Captain." Miller studied James's plans for another moment, then nodded slowly. "It's unorthodox, but the engineering is sound. I think he can actually do it. The question is whether we can spare the manpower, and whether headquarters will accept such extensive non-standard repairs." "I'll handle headquarters," Thornton said. "Hartford, you have your approval, but I want daily progress reports, and I want Captain Miller reviewing every major decision. Understood?" "Understood, sir," James replied. The reconstruction of Captain Anderson's aircraft became the most ambitious project James had ever undertaken. He assembled a team of 8 mechanics and 2 other engineers, selecting men who had shown creativity and skill in their regular work. Sergeant Chen became his second in command, managing the day-to-day work, while James focused on solving technical problems and fabricating critical components. The work took place in a corner of the main hangar, partially shielded by canvas curtains so that the regular maintenance work could continue uninterrupted. But word spread quickly about what was happening behind those curtains, and James found himself receiving visitors from across the base and even from other units. Pilots wanted to see the aircraft that was supposedly being rebuilt from scrap and salvage. Engineers came to observe the techniques being used. Even the base commander, Colonel Richard Harrison, a 52-year-old career officer who had served in the previous conflict, stopped by to watch the work progress. The removal of the damaged engine took 2 full days. The mounts had been twisted by impact, and several bolts had to be cut because they couldn't be removed normally. Once the old engine was out, James and his team began fabricating the custom mounting structure that would allow them to install the replacement engine from the crashed training aircraft. This was precision metalwork of the highest order. The mounting had to be strong enough to handle the engine's weight and the tremendous forces generated during operation, yet it had to fit precisely within the existing space and align correctly with the propeller shaft and aircraft structure. James spent 3 days in the machine shop, working with raw aluminum and steel, measuring and cutting, drilling and filing, checking and rechecking every dimension. Corporal David Kowalski, a 22-year-old machinist from Pennsylvania who had been working in his father's shop since he was 10 years old, assisted with the fabrication. The 2 men worked in a kind of synchronized rhythm, Kowalski often anticipating what James needed before he asked for it. As they worked, they talked about machinery and manufacturing, about the challenge of creating something functional from limited resources. "My dad used to say that any decent machinist can work with perfect materials and new equipment," Kowalski said as he carefully milled a mounting bracket to exact specifications. "The real test is what you can do when everything's worn out and nothing fits quite right." He'd love this project. Making something good from stuff everyone else threw away, that's real craftsmanship. When the custom mounting structure was finally complete and installed, the team carefully lifted the replacement engine into position using a portable crane. James had calculated the weight and balance precisely, but there was still a moment of collective breath-holding as the engine settled onto its new mounts. Bolts were inserted, tightened to exact specifications, checked and double-checked. Fuel lines were connected, electrical systems were integrated, control linkages were adjusted. It took another full day to install and properly adjust the modified propeller, ensuring that it was perfectly balanced and aligned. When they finally started the engine for the first time, everyone in the hangar stopped what they were doing to listen. The engine caught on the 3rd attempt, coughing briefly before settling into a steady roar. James monitored the gauges carefully, checking oil pressure, temperature, fuel flow, electrical output. Everything was exactly as it should be. Sergeant Chen stood next to him, grinning broadly. "That's one sweet sound, Lieutenant. I wasn't sure we could actually pull this off, but we did it." "1 engine down, 1 to go," James replied, though he was smiling as well. "Plus the wing repairs, the landing gear, the control systems, and about 100 other things." The wing repairs proved to be even more challenging than the engine replacement. The damage had compromised several ribs, the structural members that ran perpendicular to the main spar and gave the wing its shape and strength. James fabricated replacement ribs using aluminum sheet and angle stock, carefully bending and riveting the material to match the wing's precise airfoil shape. Lieutenant Sarah Mitchell, a structural engineer who had joined the base 2 weeks earlier, volunteered to assist with the wing repairs. She was one of only 3 female engineers in the entire theater of operations, having fought hard to be assigned to an operational unit rather than a desk job in London. She had a degree in aeronautical engineering from MIT and a perfectionist's attention to detail. "Your fabrication technique is interesting, Lieutenant Hartford," she said on her first day working on the project, examining one of the replacement ribs James had made. "Not exactly textbook, but structurally sound. You're using more material than the original design, which adds weight. But you're also creating stronger joints. It's a reasonable trade-off." James looked up from his work, pleasantly surprised. "Most engineers I've met would say I'm doing it wrong because it's not exactly like the original." Mitchell smiled. "Most engineers are taught to follow existing designs without questioning whether those designs are optimal. I was fortunate to have professors who encouraged creative problem-solving. The best engineering isn't about following rules, it's about understanding the principles well enough to know when rules can be broken and when they can't. Over the next 2 weeks, James and Mitchell worked closely together on the wing repairs, developing a mutual respect based on shared competence and complementary skills. Mitchell's theoretical knowledge combined with James's practical experience created a powerful synergy. They developed new techniques for reinforcing damaged structures, methods for testing repairs without sophisticated equipment, and approaches to documentation that would allow other maintenance units to replicate their work. The landing gear proved to be one of the most difficult challenges. The impact damage had bent the main support strut, and the wheel assembly had been knocked out of alignment. Straightening the strut required careful application of heat and pressure, a process that could easily weaken the metal if done incorrectly. James spent hours studying metallurgy references, consulting with other mechanics who had experience with this type of work, and practicing on scrap pieces before attempting the actual repair. When he finally heated the damaged strut to the correct temperature, using nothing more sophisticated than a careful eye and years of experience reading the color of hot metal, and applied pressure using a hydraulic jack and carefully positioned supports, the entire team gathered to watch. The strut bent slowly back into its correct position, and when James finally allowed it to cool and took measurements, it was within 2 millimeters of the original specifications. "That's well within acceptable tolerances," Captain Miller confirmed, reviewing James's measurements. "I'm impressed, Lieutenant. That's precision work using fairly crude equipment." "Crude equipment is all we usually have." "Sir," James replied, "you learn to make it work." By early August, after 7 weeks of intensive work, the aircraft was nearing completion. Both engines were installed and running smoothly. The wing repairs were complete and had passed structural testing. The landing gear was functional. Control systems had been rebuilt and adjusted. The fuselage had been patched and reinforced. Hundreds of smaller repairs had been completed, each one documented, each one tested. Major Thornton conducted a final inspection, walking slowly around the aircraft, examining the work, asking questions, testing components. Captain Anderson, who would be flying the aircraft if it was approved for return to service, accompanied him, equally thorough in his examination. When they finally finished, both men were shaking their heads in amazement. "Lieutenant Hartford, this is extraordinary work," Thornton said. "If I didn't know better, I'd say this aircraft just came from a maintenance depot, not a field workshop using salvaged parts and improvised materials. How confident are you that it's truly airworthy?" "Very confident, sir," James replied without hesitation. "Every repair has been tested individually, and we've done complete systems checks. The structural reinforcement actually makes it stronger in some areas than it was originally. The engines are running perfectly. All control systems respond correctly. It's ready to fly." Anderson looked at James with a mixture of respect and slight apprehension. "You understand that I'm trusting my life to your work, right? If something fails at altitude or during combat maneuvers, there won't be time to fix it." "I understand completely, sir," James said seriously. "I wouldn't recommend we fly this aircraft if I had any doubts about its safety. I've put everything I know into these repairs. It's sound." The test flight was scheduled for August 10th. The entire squadron turned out to watch, along with mechanics and engineers from across the base, and several visiting officers from headquarters who had heard about the rebuilt aircraft and wanted to see it for themselves. James stood near the runway with his team, watching as Anderson and his crew conducted their pre-flight inspection, started the engines, and began their taxi to the runway. The takeoff was smooth and confident, the aircraft lifting off and climbing into the clear morning sky. For the next 45 minutes, Anderson put the aircraft through a comprehensive series of tests: normal flight maneuvers, steep turns, climbs, descents, simulated combat maneuvers, single-engine operations, and finally, the most critical test of all, a full-power dive followed by a hard pull-up that would stress every structural component to its limits. James watched through binoculars, monitoring every movement, looking for any sign of problems, but the aircraft performed flawlessly, responding to controls smoothly, maintaining stable flight, handling every maneuver with confidence. When Anderson finally brought it in for landing, the touchdown was gentle and precise. As the aircraft taxied back to the hangar, James allowed himself to release the tension he'd been holding for weeks. Around him, his team was celebrating, slapping each other on the back, grinning broadly. Sergeant Chen grabbed James's hand and shook it vigorously. "We did it, Lieutenant. We actually did it. We brought a dead aircraft back to life." Major Thornton walked over, accompanied by Colonel Harrison and several other senior officers. The base commander was smiling. Something the troops had learned was a rare sight. "Lieutenant Hartford, that was remarkable," Colonel Harrison said. "I've been in the military for 30 years and I've never seen anything quite like what you've accomplished here. I've already sent a report to headquarters, recommending that your techniques be studied and potentially implemented across other maintenance units." Captain Anderson had climbed down from the aircraft and was walking toward them, his flight helmet under his arm, a huge smile on his face. He went directly to James and extended his hand. "Lieutenant, that bird flies better now than it did when I first got it 6 months ago. I don't know how you did it, but you've given us back an aircraft we'd written off as scrap. That's 7 crew members who'll be able to continue flying missions because of your work." Over the next several months, James continued to refine and expand his techniques. He trained other mechanics and engineers, sharing his knowledge freely, developing documentation that could be used by maintenance units throughout the theater. The methods he pioneered eventually became standard practice, allowing units to keep more aircraft operational despite the ongoing challenges of limited supplies and long supply lines. But the true impact of his work became apparent in October, when the squadron received orders for its most ambitious operation yet. Intelligence had identified a critical German communication center located in northern France, a facility that coordinated defensive operations along a large section of the coast. Destroying it would significantly disrupt enemy capabilities, but the target was heavily defended, and the mission would require a maximum effort from the squadron. Thanks to James's work, the squadron was able to launch 21 aircraft for the operation, more planes than they'd ever put in the air at one time. Among those aircraft was the one that James had rebuilt, flown by Captain Anderson, who had specifically requested to participate in the mission. The operation was complex and dangerous. The formation flew low across the channel to avoid detection, then climbed to attack altitude as they approached the target. German fighters were waiting, having somehow received advance warning of the incoming strike. What followed was a fierce engagement, with aircraft from both sides maneuvering desperately, the sky filled with tracers and smoke. The attack succeeded in destroying the communication center, but the cost was high. 3 aircraft were lost entirely, their crews gone. 7 more aircraft returned with various degrees of damage. But 19 aircraft made it back to England, including Anderson's rebuilt plane, which had taken several strikes but continued flying reliably. Among the German forces defending that target was Hauptmann Klaus Weber, a 34-year-old pilot who had been flying since 1937. Weber was an experienced aviator, a competent leader, and a thoughtful man who tried to maintain his humanity despite the brutal circumstances of the conflict. After the operation, he wrote a letter to a friend back in Germany, a letter that would eventually be captured and translated by Allied intelligence. In that letter, Weber described his growing respect for his opponent's capabilities and his increasing doubts about what he'd been told about Allied forces. He wrote about the attack he'd witnessed and defended against, describing the formations of aircraft that kept coming despite losses, the precision of the attack, the clear skill of the pilots. But what struck him most was something he observed during the engagement: aircraft that showed obvious signs of extensive repair, continuing to perform effectively in combat conditions. One of the planes I engaged had patches on its wing, covering what must have been significant damage, Weber wrote. The engines appeared to be mismatched, different types, I'm certain of it, yet it flew as steadily as any factory-new aircraft. Later, after we'd broken off the engagement, I watched that same plane head back toward England with additional damage from our encounter. It maintained formation, kept pace with the other aircraft, showed no sign of significant impairment. Their mechanics must be extraordinary to keep such damaged aircraft flying. Or perhaps they have resources and capabilities we've been told they lack. I increasingly suspect we've been misinformed about many things. Weber's letter never reached its intended recipient. It was found in his quarters after his base was captured several months later, along with his personal journal and other correspondence. Those documents eventually made their way to intelligence analysts, who found them valuable for understanding German perspectives and morale. But they also revealed something else: the psychological impact of facing an opponent who refused to be limited by conventional thinking, who found solutions where others saw only problems. Back in England, James Hartford continued his work through the winter of 1943 and into 1944. His reputation spread, and he began receiving requests for assistance from other units, invitations to share his techniques with maintenance crews across the theatre. In February 1944, he was promoted to captain and assigned to a training unit where he spent 3 months teaching other engineers and mechanics the methods he'd developed. One of his students during this period was Lieutenant Robert Chen, no relation to Sergeant Michael Chen, a young engineer from California who had grown up watching his father struggle to keep a small airline operating during the Depression. Robert Chen had learned early that necessity forced innovation, that businesses survived by finding creative solutions rather than waiting for ideal circumstances. During one of the training sessions, Chen asked James a question that went beyond technical matters. "Sir, how did you develop the confidence to try repairs that everyone else said were impossible? Weren't you worried about the consequences if something failed?" James had thought about that question often. "Of course I worried. Every time I signed off on a repair, I knew that people's lives depended on my work. But I also knew that if I didn't try, those aircraft would just sit there grounded, useless. We'd have fewer planes available for operations, which meant increased risk for the crews who did fly because they'd have less support." The real question wasn't whether to try, it was how to try in a way that maintained safety while pushing the boundaries of what people thought was possible. "But how did you know where those boundaries were?" Chen pressed. "How did you know when you were being innovative versus being reckless?" "That's the hard part," James admitted. "It requires understanding not just the immediate repair but the underlying principles. You have to know how structures fail, what stresses components face, where the critical points are. You have to test everything, document everything, be honest about limitations. And you have to be willing to say no when something truly isn't safe, even if you're under pressure to get aircraft flying. Innovation requires judgment, and judgment comes from knowledge and experience." The training program James developed eventually became standard for maintenance personnel throughout the theatre. His techniques were documented, refined, and distributed widely. By the middle of 1944, maintenance units were routinely performing repairs that would have been considered impossible a year earlier, keeping more aircraft operational, reducing dependence on long supply lines, and ultimately contributing to operational effectiveness in measurable ways. But James's most significant contribution may have been the change in mindset he helped create. He demonstrated that technical limitations could often be overcome through creative thinking, that official procedures weren't the only path to effective solutions, that individuals with skill and determination could make a meaningful difference even within large military organizations. Other engineers and mechanics, seeing what James had accomplished, began approaching their own challenges with increased confidence and creativity. In June 1944, as Allied forces launched their massive invasion of France, James was assigned to a forward maintenance unit that would deploy to the continent to support operations there. Before he left England, Major Thornton, now Lieutenant Colonel Thornton, held a small ceremony to recognize James's contributions to the squadron's success. "Captain Hartford, your work over the past year has been truly exceptional," Thornton said, addressing James in front of the assembled squadron. "You've kept aircraft flying that should have been grounded. You've developed techniques that are now being used throughout our forces. You've trained dozens of other engineers and mechanics. But more than that, you've shown us all that limitations are often just assumptions waiting to be challenged. The squadron won't be the same without you, but the lessons you've taught us will continue to make a difference." James felt genuinely moved by the recognition. He'd spent his life dealing with people who underestimated him, who assumed he couldn't possibly be as capable as he was, who put obstacles in his path based on prejudice and narrow thinking. To be recognized for his actual contributions, to see the tangible results of his work, meant more than any medal or promotion. As he prepared to deploy to France, James took one last look at the hangar where he'd spent so many long hours over the past year. The aircraft he'd rebuilt, Anderson's plane, was being prepared for another mission. It had flown dozens of successful operations since its reconstruction, had survived additional damage and been repaired again, had proven itself reliable and effective time after time. Looking at it now, James felt a deep sense of satisfaction. That aircraft represented everything he believed about engineering and problem-solving, that with knowledge, creativity, and determination, people could overcome obstacles that seemed insurmountable. The maintenance unit James joined in France faced challenges that made the work in England seem simple by comparison. Operating in forward areas, often within range of enemy artillery, with even more limited resources and under more primitive conditions, mechanics and engineers had to keep aircraft flying while dealing with mud, cold, inadequate shelter, and the constant stress of being near the front lines. But the techniques James had developed proved even more valuable in these circumstances. Throughout the late summer and fall of 1944, James worked at a series of forward airfields, moving as Allied forces advanced into France, then Belgium, then toward Germany itself. He trained maintenance crews, helped solve particularly difficult repair challenges, and continued to develop new techniques for keeping aircraft operational under increasingly difficult conditions. One incident from this period particularly demonstrated the impact of creative problem-solving. In September, a ground attack aircraft returned from a mission with damage to its landing gear that prevented proper retraction. The problem was that the crew had to continue operations from their forward field. Moving the aircraft back to a rear area maintenance depot would take at least a week, and the squadron couldn't spare the plane for that long. James examined the damage and quickly determined that a critical hydraulic component had been damaged beyond conventional repair. The part wasn't available through normal supply channels, and fabricating a replacement would require machine tools that weren't available at the forward field. But James noticed that a nearby anti-aircraft artillery unit had a damaged gun mount with a hydraulic component that, while designed for a completely different purpose, used similar internal mechanisms. Over the next 8 hours, working in an improvised workshop, consisting of little more than a table of vice and hand tools, James disassembled both the aircraft component and the artillery component, studied their mechanisms, and determined that he could combine parts from both to create a functioning replacement. The work required precision fitting, using only files and handheld measuring tools, careful testing to ensure proper operation, and creative problem-solving to overcome multiple incompatibilities between the components. When he finally installed the hybrid component and tested the landing gear, it operated perfectly. The aircraft was back in service the next day, having been grounded for less than 24 hours. The squadron commander, a gruff colonel who rarely showed emotion, had simply stared at James for a long moment before saying, "I don't know how you do this, Captain, but I'm damn glad you're on our side." As the conflict continued into 1945, James found himself increasingly involved in training and planning rather than hands-on repair work. His techniques had proven so successful that higher headquarters wanted him to help develop doctrine and training programs that could be implemented throughout all Allied air forces. In March 1945, he was recalled to England to work with a joint Anglo-American planning group, developing standardized maintenance procedures and training curricula. This work was important, but less immediately satisfying than the hands-on repair work James loved. He spent his days in meetings, writing documentation, reviewing proposals, and coordinating with various military and civilian organizations. But he recognized the value of this work: every maintenance crew that learned better techniques, every aircraft that stayed operational longer because of improved procedures, every pilot and crew member who survived because their aircraft was properly maintained. All of that represented tangible impact from work that might seem abstract and bureaucratic. The conflict in Europe ended in May 1945, with German forces finally surrendering after years of devastating combat. James was in London when the news arrived, surrounded by celebrating crowds, feeling a complex mixture of relief, exhaustion, and reflection. So many lives lost, so much destruction, so many years of struggle. And now it was over, at least in Europe. In the weeks after the surrender, as military forces began the massive task of occupation, demobilization, and reconstruction, James received new orders. He was being assigned to a team that would examine captured German equipment and facilities, assessing their technology and capabilities, trying to understand what the enemy had been able to achieve despite their ultimate defeat. It was fascinating work that would eventually contribute to significant post-war developments in aviation and engineering. One of the facilities James visited was a repair depot near Munich that had served German air units in the final months of the conflict. Walking through the workshops, examining the equipment and techniques they had used, James was struck by both similarities and differences compared to Allied approaches. The Germans had been dealing with the same fundamental challenges: limited supplies, damaged aircraft, desperate need to keep planes operational, but their solutions had been constrained by rigid adherence to official procedures and centralized control that stifled innovation. In one workshop, James found a damaged aircraft that had been waiting for parts for over 3 months, even though the necessary repairs could have been made using locally available materials and creative problem-solving. When he asked the German mechanics who had stayed on after the surrender why they hadn't attempted improvised repairs, they looked at him as if he'd suggested something unthinkable. That would have been against regulations, one mechanic explained through a translator. Only approved parts could be used. Only certified procedures could be followed. To do otherwise would have been a serious violation. Even when the parts never came and the aircraft never flew again? James asked. The mechanic shrugged helplessly. The regulations were very clear, we had no choice. James thought about that conversation for a long time afterward. It illustrated something important about why the conflict had ended as it did. When systems became too rigid, when rules took precedence over results, when people stopped thinking creatively about how to solve problems, those systems eventually failed under pressure. The ability to adapt, to innovate, to find solutions outside established channels, those capabilities had proven decisive. In August 1945, after the conflict in the Pacific ended with Japan's surrender, James received his discharge orders. He would be returning to civilian life after more than 3 years of military service. He felt ready to go home, but also uncertain about what he would do next. The world he was returning to was different from the one he'd left, and he wasn't the same person he'd been when he enlisted. Before leaving Europe, James received one final recognition, a medal ceremony where he was awarded the Legion of Merit for his contributions to maintaining operational aircraft throughout the conflict. The citation recognized his technical expertise, his innovative problem-solving, and his training of hundreds of other maintenance personnel. But what meant more to James than the medal itself was the presence at the ceremony of so many of the people he'd worked with: Sergeant Chen, Lieutenant Mitchell, Captain Miller, Colonel Thornton, and dozens of mechanics and engineers whose lives he'd touched and who had helped make his work possible. After the ceremony, as people gathered for an informal celebration, Captain Anderson approached James with a familiar grin. He'd survived the entire conflict, flying more than 80 missions, and he'd spent most of those missions in the aircraft that James had rebuilt from salvage and determination. "You know that plane is still flying, right?" Anderson said. "They've assigned it to a training squadron. It'll probably be flying for years after they scrap newer aircraft that had less interesting histories. Every time I flew it, I thought about what you did, taking something everyone else had written off and turning it into something better than it had been originally. That's a hell of a metaphor, Captain Hartford. That's a hell of a metaphor." James returned to the United States in September 1945, landing in New York Harbor, on a grey morning that somehow seemed appropriate for such a momentous transition. He spent a few weeks in Detroit, reconnecting with family and old friends, trying to readjust to civilian life. But he found himself restless, uncertain, looking for some way to apply what he'd learned during the conflict to peacetime challenges. The opportunity came from an unexpected source. One of the engineers he'd trained in England, now working for a major aircraft manufacturer, contacted him with a job offer. The company was expanding to meet growing commercial aviation demand, and they needed experienced engineers who could solve difficult problems, who could work with limited resources, who could train others effectively. Would James be interested? He accepted the position and spent the next 25 years working in various roles within the aviation industry, as a design engineer, as a troubleshooter solving production problems, as a training director developing programs for new engineers, and eventually as a senior consultant, advising on maintenance practices and reliability engineering. Throughout his career, he brought the same creativity and practical problem-solving approach that had served him so well during the conflict. But James never forgot the lessons of those years in England and France. He understood that true engineering wasn't just about following established procedures or having access to ideal resources. It was about understanding principles deeply enough to apply them creatively, about seeing possibilities where others saw only limitations, about maintaining safety and quality while pushing boundaries. And perhaps most importantly, it was about recognizing that the best solutions often came from unexpected places and unexpected people. In 1968, James was invited to speak at an engineering conference about his wartime experiences and their application to civilian aviation maintenance. He was 63 years old by then, thinking about retirement, and somewhat reluctant to dwell on events from so long ago. But the organizers had been insistent, arguing that his story contained lessons that were still relevant. Standing before an audience of several hundred engineers, many of them young enough to have no personal memory of the conflict, James told the story of rebuilt aircraft, of improvised solutions, of the transformation from impossible to accomplished. He showed photographs of the aircraft he'd reconstructed, shared technical details of repairs that had seemed unthinkable, explained the principles that had guided his work. But what he emphasized most was something beyond technical capability. Engineering, he told his audience, is ultimately about solving problems that matter. It's about taking responsibility for outcomes rather than hiding behind procedures. It's about recognizing that creativity and judgment are just as important as knowledge and skill. And most fundamentally, it's about believing that limitations can be overcome if you're willing to think differently and work hard enough. The speech was received enthusiastically, and afterward, dozens of young engineers approached James with questions. Many of them wanted technical details about specific repairs, but several asked deeper questions about how to develop confidence, how to know when to challenge conventional thinking, how to maintain ethical standards while pushing boundaries. James spent hours that evening talking with these young engineers, sharing what he'd learned not just during the conflict, but throughout a career spent solving difficult problems. One young African-American engineer from Texas stayed until nearly everyone else had left, asking question after question, clearly hungry for knowledge and advice. Finally, he asked the question that was really on his mind. "Sir, how did you deal with the prejudice, the assumptions people made, the obstacles that had nothing to do with your actual abilities?" James thought carefully before answering. "I won't pretend it wasn't difficult. It was. Every day, in ways large and small. But I learned early on that the best response to prejudice is excellence. Not because it always changes minds, it doesn't, but because it gives you certainty about your own capabilities. When people underestimate you, that can actually be an advantage. They leave space for you to act, to prove yourself through results rather than credentials. And when you do deliver results, when you solve problems others couldn't solve, it forces at least some people to reconsider their assumptions." He paused, then continued, "But here's the most important thing I learned. Don't wait for permission to be excellent. Don't wait for someone to give you opportunities. Create your own opportunities through competence, creativity, and determination. Will you face obstacles that others don't? Absolutely. Will it be fair? No. But you can still accomplish extraordinary things if you refuse to be limited by other people's narrow thinking." The young engineer nodded slowly, clearly thinking deeply about James's words. "Thank you, sir. That helps more than you know." James retired from active consulting work in 1972, but remained involved in engineering education, serving on advisory boards, occasionally lecturing at universities, and mentoring young engineers who sought his guidance. He lived to see tremendous advances in aviation technology, seeing the industry he'd served develop capabilities that would have seemed like science fiction during the conflict. But perhaps his greatest satisfaction came from the relationships he'd maintained with the people he'd worked with during those intense years of the conflict. He exchanged letters and occasional visits with Chen, with Mitchell, with Anderson, with Kowalski, and with dozens of others whose lives had intersected with his during that remarkable period. They had shared something important: The experience of achieving what others thought impossible, of refusing to accept limitations, of making meaningful contributions to something larger than themselves. In 1986, James received an invitation to return to England for a reunion of the squadron he'd served with more than 40 years earlier. He hadn't been back to England since the conflict ended, and he was curious to see how the places he remembered had changed. The reunion was held at the same airfield where he'd rebuilt aircraft from salvage, though the base itself had been deactivated years earlier and the land returned to civilian use. Walking across what had once been the runway, now overgrown with grass and wildflowers, James found it difficult to reconcile the peaceful pastoral scene with his memories of damaged aircraft returning from missions, of long nights in the maintenance hangar, of the constant urgency and intensity of those years. So much time had passed. Most of the people he'd known then were gone now, and those who remained were old men looking back at their youth. But at the reunion dinner, as the survivors gathered to remember friends who hadn't made it home, to share stories worn smooth by decades of retelling, to celebrate the fact that they had survived and built good lives in the decades of peace they'd been granted, James felt the old connections rekindling. These men understood what he'd lived through in a way that no one else could. They'd been there, had shared the risks and challenges, had been part of something that had tested them all and proven what they were capable of. Colonel Thornton was there, now 81 years old, but still carrying himself with military bearing. He sought out James and spent a long time talking with him about the old days, about decisions that had seemed so critical then, about the aircraft James had rebuilt and the methods he'd developed. "You know, the techniques you pioneered became standard practice throughout the Air Force," Thornton said. "They taught your methods at training schools for decades, and the mindset you represented, that willingness to challenge assumptions and find creative solutions, that became part of the institutional culture. I think you changed more than just some aircraft, Captain Hartford. I think you changed how people thought about maintenance and problem solving." James appreciated the recognition, but deflected some of the credit. "Sir, I was just doing what needed to be done with the resources available. Plenty of other people were solving problems creatively throughout the conflict. I might have gotten more recognition because my work was visible, but the real story was thousands of people finding ways to make impossible things work." "Maybe so," Thornton acknowledged, "but you showed the rest of us what was possible. That counts for something." James Hartford passed away in 1994 at the age of 79, having lived to see the end of the Cold Era that had defined the decades following the conflict he'd served in. His obituary in the local newspaper was brief, mentioning his military service and his long career in aviation, but giving little sense of the real impact he'd had on countless individuals and on the broader development of maintenance practices and engineering education. But the people who had known him, who had worked with him, who had learned from him, understood his significance. At his funeral, former colleagues and students came from across the country to pay respects. They told stories of problems solved, of techniques learned, of careers influenced by his example. They remembered not just his technical brilliance, but his generous mentorship, his willingness to challenge conventional thinking, his insistence that excellence had nothing to do with credentials or background, and everything to do with knowledge, creativity, and determination. Among those attending was an elderly German man who had traveled from Munich specifically for the service. His name was Klaus Weber, the former Hauptmann who had written about encountering aircraft that showed obvious repairs, yet continued flying effectively. After the conflict, Weber had spent several years as a prisoner before being released to help with reconstruction efforts in Germany. He'd eventually become an engineer himself, working in civilian aviation, and had spent much of his career teaching and writing about maintenance practices. In the decades after the conflict ended, Weber had learned the story behind those repaired aircraft he'd encountered during the operation in October 1943. He'd read about James Hartford's work, had studied the techniques that had been developed, had incorporated many of those methods into his own teaching. When he learned of James's death, he'd felt compelled to come and pay his respects to a man he'd never met, but who had influenced his life and thinking profoundly. At the reception following the funeral, Weber introduced himself to James's family and told them about that long-ago encounter, about the letter he'd written expressing his growing realization that his opponents were more capable and resourceful than he'd been led to believe, about how learning of James's work years later had confirmed those impressions. "Your father represented something important," Weber said to James's daughter. "He showed that ingenuity and determination could overcome material limitations. He proved that creativity and knowledge could find solutions where others saw only problems. And he demonstrated that excellence has nothing to do with privilege or background. It comes from within, from character and capability. Those are lessons that remain valuable regardless of time or circumstance." The legacy James Hartford left extended far beyond the aircraft he'd repaired or the techniques he'd developed. He had shown, through consistent action over many years, that technical limitations were often just assumptions waiting to be challenged, that official procedures weren't the only path to effective solutions, that individuals with knowledge and creativity could make profound differences even within large, rigid systems. He had trained hundreds of engineers and mechanics, not just in specific techniques, but in ways of thinking about problems. He had demonstrated that excellence could come from unexpected places, and that the best solutions often emerged when people were willing to think differently and work tirelessly towards seemingly impossible goals. In the decades since James's death, aviation maintenance has continued to evolve, incorporating new technologies and materials that would have seemed magical during the conflict. Modern aircraft are maintained using computer-controlled equipment, advanced diagnostic tools, and precisely engineered replacement parts delivered through sophisticated supply chains. But the fundamental principles that James understood and taught remain relevant. Engineers and mechanics still face situations where standard procedures don't work, where required materials aren't available, where creative problem-solving makes the difference between success and failure. And in those moments, whether they know his name or not, they're drawing on lessons that James Hartford helped establish. That knowledge of principles matters more than rote following of procedures. That judgment and creativity are essential engineering tools. That limitations can often be overcome through determination and unconventional thinking. And that the best engineers are those who take responsibility for outcomes rather than hiding behind excuses. The aircraft James rebuilt from salvage and determination flew until 1953, when it was finally retired after accumulated thousands of hours of flight time. It served first in training squadrons, then in various support roles, far outlasting many aircraft that had required far less dramatic repairs. When it was finally withdrawn from service, it was already something of a legend, known throughout aviation maintenance circles as proof of what skilled engineers could accomplish with limited resources and unlimited determination. That aircraft was eventually acquired by a museum devoted to aviation history, where it was carefully restored to represent its appearance during the conflict. The museum's exhibit tells the story of James Hartford and the remarkable repairs that brought a seemingly destroyed aircraft back to operational status. Visitors can see the patches on the wing, the custom engine mounts, the improvised components that kept the machine flying, and they can read about the principles that guided the work, understanding over procedure, creativity over convention, determination over limitation. In educational programs at the museum, instructors use James's story to teach engineering students about problem-solving, about ethical responsibility, about the importance of questioning assumptions. They emphasize that while the specific techniques he used may be outdated, the fundamental approach he represented remains timeless. Engineering is ultimately about solving problems that matter, about taking available resources and creating solutions that work, about refusing to accept that something is impossible simply because it's difficult. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.